Hello class. In this video I will show you two examples on how to calculate relative humidity using the Stuve diagram that is in figure 3 of this week's lab. Before doing that though, I want to quickly review with you a couple of concepts that are fundamentals to understand why we do what we do with the Stuve diagram. So we will be working with air parcels. And an air parcel is an imaginary volume of air that is enclosed in a thin elastic cover that acts independently of the surrounding air. Independently is important. It means that as the air parcel moves through the atmosphere, it is not affected by what is happening outside the atmosphere in terms of moisture content and temperature. While this independently concept is not important, not very much important in this module, it will become extremely important in module 4. Okay, so the average size of an air parcel is about a cubic foot, which is what you see in this image right here. The humidity of an air parcel is the amount of water vapor that is in the air parcel. And this can be measured in different ways depending on what you have. So we can measure the humidity in grams per volume of the air parcel, or we can measure it in grams of moisture per kilogram of air parcel, or we can measure it in millibars. So the contribution of water vapor to the atmospheric pressure exerted by that air parcel. So we talk about absolute humidity, specific humidity or mixing ratio. They both measure grams per kilogram, grams of moisture per kilogram of air, but the kilogram of air can be dry air, so the air without the moisture, or moist air, the air plus the moisture. Okay, mixing ratio is what we're going to use today, and it's grams of moisture per kilogram of dry air. The amount of water vapor in an air parcel relative to the maximum amount that can exist in the parcel at a given temperature and pressure is called relative humidity. And relative humidity is measured in percentages, and it is what is commonly used when you watch a weather forecast. And that's because relative humidity gives us an immediate idea of how comfortable or uncomfortable conditions will be if we go outdoor, and if, for example, we want to work in the yard, go hiking, go mountain biking, etc. High humidity, you probably don't want to do it. Low humidity, even if the temperature is high, it will be much more pleasant. So let's focus on moisture in the air. The maximum amount of moisture that can exist in an air parcel at a given temperature and pressure is called the saturation value of that air parcel. So, for example, 1 kilogram of air at sea level at a temperature of 10 degrees Celsius can contain a maximum of 9 grams of moisture. So that's the saturation value for that air parcel. So 1 kilogram of air at sea level occupies approximately 1 cubic meter in volume, and 9 grams of moisture as a weight that is equivalent to about 9 dyes. Warm air is less dense than cold air because as energy is added, heat energy, the molecules in the air start moving faster and move farther away from each other. And at any given pressure, 1 kilogram of cold air will occupy a smaller volume than 1 kilogram of warm air. So in this image, you see two air columns. One is a column of warm air, about 30 degrees Celsius, and the other one is cold air, 10 degrees Celsius. This example is for the same location during the day when the sun is shining. The air in the troposphere will expand, and so This is shown by a taller column of air. At night, same location, no sun, the air cools down, and therefore the column of air shrinks. Because of this change in volume, more moisture can exist in warm air than in cold air. So if we fill this column of air with the maximum amount of moisture that can exist, we see that it's 9 grams. Once the air expands, assuming there is no change in the amount of moisture, those 9 grams of moisture will not fill the expanded water column completely. So we can actually add more moisture to the air column on the left because it is warmer. So at a given pressure, 1 kilogram of saturated warm air will contain more moisture than 1 kilogram of saturated cold air, which is what is shown right here. For example, 9 grams of moisture can exist as saturation in this air column at 10 degrees Celsius, and 17, almost double, gram of moisture can exist in 1 kilogram of air in the column on the left. Assuming that we now have air at 30 degrees Celsius with 9 grams of moisture, this is 1 kilogram of air. 9 grams of moisture do not saturate this air column, this kilogram of air. But if we cool down warm air, we can bring it to saturation. So here is 9 grams of moisture, and we cool down the air parcel and to 10 degrees Celsius in this example. We still have 9 grams of moisture, but now because the air is colder, it is saturated. So cooling air can bring it to saturation. Cooling unsaturated air can bring it to saturation. And the dew point is the temperature at which cooling air becomes saturated. So in this example, 10 degrees Celsius is the dew point temperature, which is shown with an uppercase T and a lowercase d next to it. So again, important concept. When you cool an unsaturated air parcel to its dew point temperature, the air parcel becomes saturated. This is important to understand what we do with Stuve diagrams to find relative humidity. So let's work a couple of examples. Remember, relative humidity equals mixing ratio over saturation mixing ratio times 100. So let's start with a Stuve diagram. This is the one in figure 3 of the lab. On the x-axis, we have temperatures in degrees Celsius. The vertical lines join points that are at the same temperature, and they're called therefore isotherms. The horizontal lines join points that are at the same pressure. The pressure scale is on the vertical axis, the y-axis. It's in kilopascals, but we already know that we just need to add a 0 and we get the actual atmospheric pressure is in millibars. One thing that is very helpful as you reason with this is to add the word saturation at the top of this plot right here. Okay, and this is because we will be looking for saturation mixing ratios, and putting the word right there is going to help you remember that. The slanted lines, slanted dotted lines are called isohumes, and they join points that have the same mixing ratio, or grams per kilograms of moisture per kilogram of dry air. These blue dots represent an air parcel that is at a temperature of negative 20 degrees Celsius at an atmospheric pressure of 500 millibars and with a mixing ratio of 1.5 grams per kilogram. That means that if you have a kilogram of air that is saturated, it will contain 1.5 grams of moisture. If your air weighs 2 kilograms, then it will contain 3 grams of moisture. If it is 3 kilograms, then it will contain 4.5 grams of moisture, because the mixing ratio is given as grams of moisture per kilogram of air. Let's assume that we have an air parcel at an atmospheric pressure of 900 millibars, a temperature of 22.5 degrees Celsius, and a dew point temperature of 12 degrees Celsius. What is the relative humidity? So first, notice how the temperature and the dew point temperature are different. So this tells us that we have an unsaturated air parcel, which means that if this is the air we're looking at, only portion of it, only part of it is filled with moisture. Now, the first step is to plot the air parcel. So we have a temperature of 22.5 degrees. So we're looking at this air parcel right here, and an atmospheric pressure of 900 millibars. So this is the line we're going to use. These parcels conveniently sits over a isohume, and this is telling us that if this parcel were saturated, it would contain 20 grams of moisture per kilogram of air. So that is the saturation mixing ratio for this air parcel. How much can exist in this air parcel at saturation at 22.5 degrees Celsius. Saturation mixing ratio, 20 grams per kilogram. Now we need to find out how much moisture is actually in the parcel. And the way to do it is to virtually cool the air parcel to its dew point temperature, which is when it becomes saturated. So the dew point temperature is 12 degrees Celsius. The atmospheric pressure doesn't change. So you simply move the air parcel toward colder temperatures and plot it at a temperature of 12 degrees Celsius. So you cool it down until it reaches saturation. So there it is. That's our air parcel at saturation at 12 degrees Celsius. Well, again, it conveniently sits on a isohume, and so we can find how many grams of moisture are actually in the air parcel. So that is the mixing ratio, the actual amount of moisture that is in the air parcel, which is 10 grams per kilogram of air. So we can now calculate relative humidity, which is 10 over 20 times 100, and that is 50%. So let's consider another example. We have an air parcel at a pressure of 500 millibars and at a temperature of -6 degrees Celsius. A dew point temperature of -25 degrees Celsius. What is its relative humidity? First of all, notice that there is a difference between the temperature and the dew point temperature. So what this is telling us is that the air parcel is unsaturated, and therefore it's only partially filled with moisture. There is room for more moisture in this air parcel. So the first thing we're going to do is to plot the air parcel. It has a temperature of -6 degrees. So we're looking at this isotherm here, and it has a pressure of 500 millibars. So we're looking at this isobar here. Okay, so let's plot the parcel. There it is. In this instance, the parcel is not falling on a isohume. It's not falling on one of these lines here. So what do? Well, we draw a line from the air parcel following the isohumes and reaching the axis right there. Okay, so here it is. It falls in between 4 and 6, so we estimate that the mixing ratio for this air parcel right there is 5 grams per kilogram. And this is what you're going to get in the test, in the quizzes. If it is in between, it is the number in between. I'm not testing you for your ability to estimate, but for your understanding of the procedure that you need to use to find out relative humidity. So in this case, we have a saturation mixing ratio for the air parcel that is 5 grams per kilogram. This is how much can exist in the air parcel if the air parcel were saturated. But we know that it isn't. So now we need to find out how much moisture is actually in the parcel. And to do this, what we need to do is to virtually cool the atmospheric parcel. So we keep it at the same pressure, but we shift it to the left to a temperature of negative 25 degrees Celsius. By cooling down the air parcel to its dew point temperature, we saturate the air parcel, and once the air parcel is saturated, we know how much moisture is in it. So negative 25, still 500 millibars, that's our parcel, and the mixing ratio is 1 gram per kilogram. So now we have mixing ratio, saturation mixing ratio. We can calculate relative humidity, which is 1 over 5 times 100, that is 20%. So that will be it for today. Thank you for listening.